In this tutorial, we shall familiarize ourselves with tie constraints. Tie constraints are surface-based constraints. They can be used to simulate two parts stuck together or fused together, whether it be with adhesives, rivets, fasteners, welds, or other methods. The tie does not model the actual mechanism of the sticking, just the fact that it exists. Each node on the slave surface is constrained to have the same motion as the node on the master surface to which it is closest, so that their translational degrees of freedom are constrained and possibly their rotational degrees of freedom as well. The tie can transfer mechanical loads, temperatures, pore pressures, acoustic pressures, or electrical potential, just as if the two parts really were fused together. Tie constraints also allow dissimilar meshes to meet each other. When you mesh different regions of a part with different mesh sizes or densities, Abaqus automatically generates tie constraints between the mesh surfaces. This allows easy mesh refinement with rapid changes in mesh densities. We will demonstrate tie constraints using a sandwich structure. A sandwich structure consists of two plates with a web or core sandwiched between them. Generally, the plates are very thin with a thick core, but in this demonstration we won't focus on their dimensions, but rather on the process of using tie constraints. We shall refer to the plates as the top layer and bottom layer, and the core as the core layer. The plates of a sandwich structure can be fixed to the core using adhesives, welds, fasteners, or other methods. In this example, we do not wish to model the adhesive, fastener, or weld, just the fact that the surfaces are constrained together. The tie constraint will be ideal for our purposes. The dimensions of the parts are displayed in the figure. They are in SI units with length in meters. The wall thickness for the core cells is 0.04 meters, meaning that the distance between the holes and also the distance between the holes and the edge of the layer is 0.04 meters. All three parts are made of AI-SI 1005 steel with a density of 7,800 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. All three layers of the sandwich structure will be fixed at one end, making it a cantilever. A uniform pressure load of 10 newtons per meter squared, or 10 pascals, will be applied on the top surface, causing the structure to bend downwards. Let's proceed with the demonstration. Open a new model in Abaqus. Rename it Sandwich Structure. Create a new part named Top Layer, which is a 3D deformable solid extrusion. Set the approximate size to 2. Use the Create Lines Rectangle tool and the Add Dimension tool to sketch the part. Create another part called Core Layer, which is also a 3D deformable solid. Once again, use the Create Lines Rectangle tool and the Add Dimension tool to sketch the part. We shall use the Create Cut Extrude tool to cut rectangular holes and create the core cells. Abaqus prompts you to select a plane for the extruded cut. Select the top surface of the core. You are then asked to select an edge or axis that will appear vertical and on the right. Choose the appropriate edge to proceed. You will find yourself in the sketcher. Use the Create Lines Rectangle tool to draw 6 rectangles. Dimension the first one using the Add Dimensions tool. Click the Add Constraint tool. We will use the equal length constraint to make the lengths and widths of all holes equal. Set the distance from the top edge of the first hole to the top edge of the core layer to be the wall thickness, or 0.04 meters. We can then use a coincident constraint to make all the corresponding edges of the holes line up with each other. Set the distance from the other edge of the first cell to the edge of the core layer to be 0.4 meters. Set the wall thickness between each cell to match this as well. Now that the section for the extruded cut has been sketched, click Done. Ensure that the extrusion arrow points into the core layer, otherwise click the Flip button. Set the extrusion type to Through All. The cut extrusions are created and our core layer is ready. While the core layer is exactly as we need it to be, we could have constructed it more easily using patterns. Let's demonstrate that while we've got the opportunity. We'll delete the current cut extrusion and rebuild it with a pattern. Expand Core Layer in the model tree and expand the Features container. Right-click Cut Extrude 1 and delete it. Once again, choose the Create Cut Extrude tool and follow the same procedure as before to reach the sketcher. Sketch and dimension the first rectangle. Also set its distance from the two edges of the core layer to 0.04 meters. Click the Linear Pattern tool. Abaqus prompts you to select the entities to pattern. Select the rectangle. In the Linear Pattern dialog box, we can control how the pattern replicates in the vertical and horizontal directions. We need 6 columns and 1 row. Note that the spacing for the pattern in the horizontal direction is not just the thickness of the wall between the cells, but the distance from the left edge of a cell to the left edge of the next cell. So it's the cell width of 0.087 plus the wall thickness of 0.04, which gives us 0.127. The preview allows us to see the pattern update in real time. Click Done. As you can see, using a pattern accomplished the same goal as drawing the cells one by one, and it was a lot quicker. Create the bottom layer in the same manner as the top layer. Create the material AISI 1005 steel. Give it a mass density of 7,800 kilograms per meter cubed. For its elastic properties, set the Young's modulus to 200 gigapascals and the Poisson's ratio to 0.29. Create a solid homogeneous section called top layer section. Assign it the steel material. Similarly, create core layer section and bottom layer section. Since we're assigning the same material to each section, we might as well have just created one section in this demonstration. However, quite often with sandwich structures, you use different materials for the different layers. If you later decide to experiment with different materials as part of your analysis, it will be easier to assign different materials to each layer since they're already associated with separate sections. Assign the sections to their corresponding parts. It's time for assembling. Create a dependent instance of the top layer. Then create an instance of the core layer. By default, Abaqus positions instances in the assembly at the same coordinates as the local coordinates of the part. Since both our parts were created at the origin, they overlap each other in the assembly. Hence check Auto Offset from other instances, and Abaqus will automatically move the core instance to a suitable location. Let's create assembly constraints for these two part instances using the Create Constraint face-to-face tool. It might be hidden behind the Create Constraint parallel face tool. Abaqus prompts you to select the planar face or datum plane of the instance that will be moved. Select the bottom face of the top layer instance. Abaqus then prompts you to select the planar face or datum plane of the instance that will remain where it is. Click the top face of the core layer instance. Abaqus will display arrows on both faces. It will inform you that the instances will be constrained in such a way that the arrows point in the same direction, and will give you the option to flip it. Since the arrows for the correct faces are not already pointing in the same direction, we click Flip. Now that they point in the same direction, we can click OK. Set the distance between the two faces to 0 so that they will be touching once placed over one another. Use face-to-face constraints 2 more times to place the top layer instance on top of the core layer instance. Repeat the process for the bottom layer. Let's create sets for 2 nodes where we wish to obtain displacement history output. In the assembly container, double-click Sets. Name the set Displacement Point 1. Abaqus prompts you to select the geometry for the set. We would like to select a point on the inside of the core cell closest to the free end. However, we cannot select it as it is hidden by the bottom layer and the core layer itself. To make it visible, we shall use the Display Group toolbar. Click the Remove Selected tool in the toolbar. For the entities to remove, use the combo box to set it to instances. Click on the bottom layer instance to remove it. You can now select the node for the set. Click Replace All to make the bottom layer visible again. Similarly, create another set for the corner of the bottom layer instance. We need to create a step for the analysis. We call it Apply Load and set it to type Static General. Turn on MLGeom for nonlinear geometry. We will not create any field output requests, however we will create history output requests. Right-click on HOutput1 and choose Rename. Set the name to Displacement Output 1. Double-click on Displacement Output 1 to get the Edit History Output Request window. Change the domain to set and choose Displacement Point Set 1 as the set. For the output variables, select UT, which is translations. Similarly, create a history output request displacement output 2 for the set displacement point set 2. Now come the boundary conditions. Create one called fix top layer end. It is active from the initial step. Fix one end of the top layer using an Encastor boundary condition. Similarly, create fix core layer end and fix bottom layer end. Let's create the load. We'll call it Uniform Applied Pressure. Activate it in the Apply Load step and set it to type Pressure. We shall apply it on the top surface of the top layer and give it a magnitude of 10 newtons per meter squared. At this point, we should identify and name the surfaces that will be tied together so that it will be easier to create the tie constraint. Let's create some surfaces. Expand the assembly container in the model tree and double-click Surfaces. Name the surface Top Layer Bottom Surf. It is hard to select the bottom of the top layer in the viewport since the core is underneath it. One way to make it visible might be to temporarily suppress the face-to-face constraints between the rectangular block and the plank. A better way is to use the Display Group toolbar, as we did a little earlier, to hide everything under the top layer. Similarly, define the surfaces bottom layer top surface, core layer bottom surface, and core layer top surf. We shall now define the tie constraints. Double-click Constraints in the model tree. In the Create Constraint dialog box, name it Tie Constraint 1 and choose Tie as the type. For the master type, choose Surface. The surface can be selected in the viewport, but we have already defined surfaces in the previous step, so click the Surfaces button. We will set Core Layer Top Surf as the master surface. Check Highlight Selections in Viewport to ensure that we are picking the correct surface. For the slave type, once again choose Surface. Set Top Layer Bottom Surf as the surface. The Edit Constraint window is displayed. Here you can see the selected master and slave surfaces and switch them if desired. Just as in the case of contact interactions, tie constraints can be surface to surface or node to surface. The internal formulations, as well as the advantages and disadvantages of these two discretization methods, were discussed in the contact modeling tutorial, and the same principles apply here as well, with a few minor differences. To refresh our memory, a surface-to-surface approach enforces constraints in an average sense over a finite region rather than at discrete points, and multiple master nodes are used. The surface-to-surface tie constraint differs from the surface-to-surface contact in that each surface-based tie constraint involves only one slave node, whereas contact involves multiple slave nodes. As with contact, the surface-to-surface formulation results in a more uniform distribution of pressure and less stress noise at the tied interfaces compared to node-to-surface. The disadvantage is that it's not as efficient as node-to-surface. Node-to-surface, on the other hand, is more efficient. However, the forces will tend to concentrate at the nodes, leading to spikes and valleys in the stress distribution. The discretization method combo box gives you three options: Analysis Default, Node-to-Surface, and Surface-to-Surface. Analysis Default will use the default discretization method for the solver, which is Surface-to-Surface for Abaqus Standard and Node-to-Surface for Abaqus Explicit. The position tolerance determines whether or not individual nodes of the surfaces get tied together or not. If the slave and master surfaces are close enough, meaning that the distance between them is less than the tolerance, the nodes will be tied and will remain tied for the rest of the simulation. We shall use the computed default position tolerance here, but you have the option to specify a tolerance manually. Adjust slave surface initial position tells Abaqus to move all the nodes of the slave surface onto the master surface in the initial configuration before running the simulation. This ensures that all the surface nodes are tied. Otherwise, if the gap between them exceeds the position tolerance, these nodes will not be tied, and this may cause some inaccuracies. We shall leave this option checked. Tie constraints always constrain the translational degrees of freedom of the nodes of the tied surface to be the same. However, the analyst has the option of specifying whether or not the rotational degrees of freedom should also be tied. We shall leave this option checked as well. Similarly, create Tie Constraint 2 to tie the top surface of the bottom layer with the bottom surface of the core. Let's mesh the parts. All three layers should be meshed with 8-node linear brick elements with reduced integration. The approximate global seed size should be set to 0.04. Create a job called sandwich structure job and run it. View the results of the simulation. When you try to plot the deformed shape, there does not appear to be any deformation. This is because nonlinear geometry was specified when defining the step, and when NLGeom is used, Abaqus automatically sets the deformation scale factor to 1. Since we use a very small pressure load on a steel structure, there is little visible deformation. We will need to set a very large deformation factor to see anything. Click the Common Options tool. Set the deformation scale factor to a uniform value of 1 million. You will now be able to see the deformation when you view the deformed shape. We will now save the XY data and report it. Expand sandwich structure job.odb in the output database tree. Expand history output. We want the U2 displacements of the bottom layer and core layer at the nodes we have defined using sets. Right-click on each of them and choose Save As. Name them Sandwich XY Data 1 and Sandwich XY Data 2. Go to the Report menu and choose XY. Choose Sandwich XY Data 1 in the XY Data tab. In the Setup tab, next to File Name, click Select. Create a folder called Sandwich located in the C drive and store the report in it as sandwichxydata.txt. Uncheck Append to File so that if the file already exists, it will be overwritten rather than appended to. In the Data section, choose to report the column totals and column min-max as well. Repeat the process for Sandwich XY Data 2 as well, but this time check Append to File, so both datasets will be reported in the same file. Using Windows Explorer, navigate the Sandwich folder in the C drive and view the contents of sandwichxydata.txt. You see that the nodal displacement history for the two sets has been written to the report.